Welcome back everyone. In this lecture I will begin the theory of abstract root systems. So, ultimately we would like to classify all finite root systems. So, let us first recall the definition of this root system. So, we already saw that this root system actually naturally comes from the theory of semi-simple algebras. Anyway, we will just first write down all the important properties and then make the definition. So, we will actually fix some notations. We denote E by the Euclidean space. So, this is Euclidean space. So, that means E is finite dimensional real vector space equipped with an inner product, So, that is actually positive definite bilinear form. So, this inner product we just denote it by just bracket comma bracket. So, because this is a positive definite bilinear form, if we take any x in E and then we have this inner product x is 0 if and only if x is 0. And we know that for any x in E, the inner product xx must be always greater than or equal to 0. So, these two conditions must be true. So, in particularly we can use all the information that we know about Euclidean geometry. Okay. So, that is something we will be repeatedly using. So, what is special about working in the Euclidean space? So, now let us recall the formula that actually we got between two roots. Okay, if we take alpha and beta, so these two are roots. So, then we saw that beta minus beta of h alpha. So, or otherwise it is in terms of the inner product, it is actually exactly beta minus twice beta alpha divided by alpha alpha alpha. So, we saw that for alpha beta roots, beta minus this twice beta alpha divided by alpha alpha alpha, this also must be a root. So, this formula in some sense actually possesses lots of information about these roots. So, let us closely look at this formula and then see what this formula actually tells in terms of the transformations. So, if we take this gamma inside capital E and then this alpha inside phi, so then we can define this following map. So, this following map which we denoted by S gamma of alpha, S alpha of gamma. So, what is this map S alpha of gamma? So, that is given by this formula gamma minus twice gamma of alpha divided by alpha alpha alpha. So, now look at this formula. So, this formula definitely defines linear transformations on this capital E. So, it is not hard to see this is indeed actually a reflection with respect to alpha. So, what I mean by reflection? So, you can see that this is definitely reflects the hyperplane that is perpendicular to this alpha. So, let us denote P alpha by those x in E such that this x comma alpha is 0. So, that means this is a plane that is perpendicular to this alpha. So, the hyperplane that is perpendicular to alpha. So, now what happens if you look at this formula star? So, then you can see that easily that S alpha of gamma. So, that will be gamma if gamma actually comes from this P alpha, because this gamma alpha, this inner product will be 0. So, that means S alpha gamma will be gamma. So, that means all the points that are on this plane, so which is P alpha, so those are all fixed. Now, this alpha is actually going to be a vector which is perpendicular to this P alpha. So, you can see that this S alpha of alpha. So, if you substitute in the formula, you can see that you get minus alpha. So, because when you do this reflection with respect to this P alpha, so this alpha must be mapped to minus alpha. So, S alpha of alpha you can see from the formula. So, this alpha minus twice alpha comma alpha divided by alpha alpha comma alpha. So, that means this is going to give us minus alpha. So, that means you can see that the reflection with respect to this hyperplane P alpha uniquely determined by these two formulas. So, since S alpha is actually that is given in this star satisfy these conditions. So, that means this S alpha must be a reflection with respect to this P alpha. So, S alpha, this is the reflection. So, with respect to the hyperplane P alpha. So, in order to actually give this P alpha, it is enough to say what is alpha. So, note that scaling this alpha will not change the reflection. So, S alpha will be same as S of C alpha for all C coming from real numbers which is not 0. Okay. So, what this means? This means, so if we take alpha beta in phi, so then if we look at S alpha of beta, which is the reflection defined using alpha, and then that acts on this beta, that must be inside phi. So, this is an important condition. So, that tells that these reflections play a vital role in the theory of this root system. Okay. So, here we have this reflection and we observe that S alpha must be equal to S C alpha. So, now we will actually define so what is the root system using these reflections. So, here is the definition which is motivated from the set of roots that we have seen from the theory of semi-simple Lie algebras. But again, like we just take the properties that are satisfied, and then we will see that those properties more or less determines the root system and as well as the corresponding semi-simple Lie algebras. Okay. So, what are all those properties which is already I listed, but anyway let me recall. So, we say a subset phi of E is actually a root system. First of all, we take it to be finite subset. Okay. A subset phi of E, it is said to be a root system. So, it must satisfies the following conditions. If it satisfies the following condition, what are those conditions? First condition is phi must be finite and 0 is not in phi, and the span of phi over real, that must be capital E. So, because this is sitting inside the Euclidean space, it is a spanning set, that is what it says. The second condition, if we take alpha, so then the only multiple of alpha must be plus or minus alpha. If alpha is in phi, so then the only multiple of alpha that are in phi are plus or minus alpha. The third condition, so this is just says that if alpha is in phi and C alpha is in phi, then that should imply C must be plus or minus 1. The third condition, which is about this reflection, if alpha and beta is in phi, so then what we do, we take this S alpha of beta, which is the reflection with respect to alpha applied on beta. So, which is by definition beta minus twice beta alpha divided by alpha alpha alpha. So, this is the algebraic formula for the reflection. So, then this must be again a root inside phi. The fourth condition, so this is called crystallographic condition. So, which is actually motivated from the root system that pops up from this semi-simple Lie algebras. So, what is this crystallographic condition? So, that is actually about the integrality of this Cartan numbers. So, if alpha beta is in phi, so then this number that we are interested in, so this 2 beta alpha divided by alpha alpha, so that must be an integer. So, this twice beta alpha divided by alpha alpha, this must be integer. So, these numbers will be called Cartan numbers or integers. Okay. So, because this notation is going to be again and again used. So, we just simplify this as this angled beta comma alpha. So, the angle beta comma alpha defined to be this Cartan number twice beta alpha divided by alpha alpha. So, this is the definition of this angle beta comma alpha. So, in general, if we actually assume this condition, the only multiple of alpha that are in phi are nothing but plus or minus alpha. So, this condition is actually naturally motivated from for the roots that are coming from semi-simple algebra. So, this condition will be called reduced condition. Okay. In literature, we can see that root system actually pop up in many places, many different places in Lie theory. For example, it is also actually comes naturally from the theory of finite reflection groups. And not only that, there are other places like affine Lie algebras and so on, this root system naturally pop up. So, there we have to consider somewhat more general setting. Okay. If this condition second condition is actually called what is called reduced root system. So, in literature the condition 2 will be dropped, that will be called non-reduced root system. Of course, in this course we will not consider non-reduced root system. And of course, this condition 4, that is called crystallographic condition, which is again naturally motivated from the roots that we come across from the semi-simple Lie algebras. But again, like I said, when we consider root system that comes from finite reflection groups, this crystallographic condition won't be satisfied. So, in that case we just consider root system without this 4. But anyway, in this course whenever we say root system, we always mean the root system that satisfy this condition 1 to 4. So, in literature it is called crystallographic reduced root system, but we will not get confused, we just call this as root system. So, now you can see that once we have defined root system, then there is a natural group that is actually associated with root system. So, that is generated by all the reflections that comes from this alpha in phi. Okay. So, we denote this W or the W of phi. So, once the phi is understood, we just take it to be W. So, that is going to be the subgroup of GL of E, which is generated by all this reflection S alpha, where alpha coming from phi. So, this is clearly subgroup of GL of E, which is set of all invertible transformations, invertible linear transformations from E on to E. Okay. So, now it is easy exercise to check, I will leave it to you to check that S alpha inverse is actually S alpha. So, that means S alpha is an involution inside GL of E. So, S alpha in particularly inside GL of E. So, we can talk about this W, which is subgroup generated by all the reflection that comes from this set of roots phi. So, this W is actually called the Weyl group. This is the Weyl group of phi. So, if we go back to the condition 3, so what this condition 3 says, so if we take any reflection S alpha, then S alpha of phi must be equal to phi. So, that is what condition 3 says. So, the root condition R3 implies that S alpha of phi is actually subset of phi. Since S alpha is invertible, this is actually going to give us, because phi is finite, S alpha phi must be equal to phi. Okay. So, now it is clear that W also maps phi to phi. So, any element of W. So, W of phi maps phi into phi for all W in W, as W is generated by S alphas, alpha is in phi, and for generators we have this condition. So, that means W naturally acts on this phi. So, now let us look at this action. So, what is the meaning of naturally acts? So, that means W permutes all the elements of phi. Okay. So, W permutes all the elements of phi. So, in particularly we have a natural map, let us call it pi, from W to this S of phi. So, this is the symmetric group on phi, symmetric group on phi. So, that means all bijective maps from phi to phi. So, the map is defined to be, you take W and then send it to, so W just permutes phi to phi. So, then you just send it to that permutation W of phi. Okay. Note that this map is actually injective map. So, I will leave it to you to check. This is a group homomorphism. So, that is not very hard to check. So, pi is a group homomorphism. So, that follows from the fact that W acts on phi. So, now what kind of group homomorphism it is? You can see that since phi spans entire space capital E, this pi must be injective map. Okay. So, pi is injective since span of phi is equal to identity. So, let us prove this fact. So, this is easy to prove. Suppose W fixes all alpha for all alpha in phi. So, that means W is in the kernel of pi. So, then that implies W actually fixes all the span of phi. So, Wx will be x for all x inside span of phi, but the thing is span of phi is capital E. So, that implies W is actually identity on E. So, that forces that this pi is injective. So, that means W is embedded inside this S phi. So, since S phi is finite group, so that forces that W is also a finite group. So, we have defined this W in a way like abstract group generated by these reflections S alpha, alpha coming from phi. So, a priori it may not be finite group, but we proved that since span of phi is E. So, this must be actually a finite group. So, now let us closely understand more about this group. So, for that purpose we need to actually recall some of the interesting facts about some element of GL of E that acts on this capital E, which leaves phi invariants. So, let us make this important general remark, so which I will call it lemma, and then using that we will understand the action of W more on capital phi. So, the lemma 1, what it says, so you start with phi being a finite set which spans E. For example, you can take it to be a root system, not a problem. So, let phi be a finite set that spans capital E. So, now what we do, we take all the reflections that comes from these elements of phi. We assume that this phi is invariant under those reflections. Suppose S alpha phi is equal to phi for all alpha in phi. So, let us assume this. So, then if we have this some element sigma which is inside your GL of E. So, let us say this actually leaves your phi invariant. So, that means sigma of phi is equal to phi. And also assume that it fixes a hyperplane. So, it fixes pointwise a hyperplane. So, that hyperplane let us call it capital P of E, and assume that this also sends some non-zero alpha in phi to its negative. So, it also sends some non-zero alpha in phi to its negative. So, then we prove that this sigma must be S alpha for some that particular alpha in phi, and this P also, the hyperplane also must be equal to P alpha. Okay. So, you may wonder actually why such a lemma that we need. So, we will see many applications of this lemma later. For example, one of the applications using this lemma we can understand all the reflections that are in W. Okay. For example, if you start with the reflection sigma inside your W, then since W leaves phi invariant, so that sigma satisfies all the properties of this lemma. So, because so in particularly one can actually try to prove that sigma is actually S alpha for some alpha in phi. So, that is indeed kind of says that. So, S alphas are the only reflections that are in W. Okay, we will actually come to that conclusion later, but anyway. So, this is about some sigma that is acting on phi that fixes a hyperplane P and sends some alpha to its negative, then that sigma, what we can say is that sigma must be S alpha, that is what we are saying. So, how do you prove such statement? So, let us try to see. So, to prove this statement sigma equal to S alpha, it is enough to prove that sigma S alpha is actually identity. So, for that purpose we just take tau to be sigma S alpha. Note that this is same as sigma of S alpha inverse, because S alpha is involution. So, now since S alpha sigma both leaves phi invariant, you can see that tau of phi is also phi. So, that is very clear. So, now if you compute what is tau of alpha, so that is going to be sigma S alpha of alpha, which is going to be sigma of minus alpha. Since sigma maps alpha to minus alpha, so it is going to be plus alpha. So, that means tau of alpha is equal to alpha. So, tau leaves alpha invariant. So, now if we take this capital E, you can see that this capital E can be written as P direct sum R alpha, because sigma fixes all the elements of P and sigma maps alpha to minus alpha. So, that means elements of P and R alpha, they are all linearly independent. So, that makes it E equal to P direct sum R alpha. So, similarly, you can also see that P alpha and alpha, they must be linearly independent. So, then that makes P alpha direct sum R alpha is also capital E. So, in particularly if we consider this space capital V, which is nothing but E modulo R alpha. So, then we can make this sigma as well as S alpha to act on this capital V. Since sigma of alpha is minus alpha and then S alpha of alpha is also minus alpha. So, that actually allows us to make the sigma and S alpha to act on this capital V. So, note that sigma and S alpha act on this capital V. So, let us compute how it acts. So, indeed we want to compute the action of tau on this V. Okay. So, this implies, so tau act on this capital V. Note that tau of alpha is already alpha. So, because tau of alpha is alpha, so tau naturally act on capital V. So, we will just use this information and then compute how tau acts on this capital V. So, for that purpose let some V bar inside capital V. So, then you can write this V bar as V plus R alpha for some V in your capital E. So, now since capital E is nothing but P plus R alpha. So, you can write this V as some elements from P and then some C times alpha, where P is coming from capital P and C is coming from R. So, that you can see that this is exactly equal to V bar equal to P plus R alpha. Similarly, this V is also coming from capital E, which is P alpha plus R alpha. So, then you can already write this V as some P alpha plus some D alpha, where P alpha coming from capital P alpha, D coming from this R. So, then you can see that this also can be written as P alpha plus R alpha. So, now let us compute what happens if we apply S alpha of V bar. So, S alpha of V bar will be exactly equal to S alpha of P alpha plus R alpha, because we know the action of S alpha on P alpha, that is why we just use the second representative. So, then that says S alpha P alpha must be P alpha, because S alpha fixes all the elements in capital P. So, then we get S alpha of V bar equal to P alpha plus R alpha. So, that means this is exactly equal to V bar. So, similarly, we can see that if we take tau of V bar, which will be sigma of S alpha of V bar. So, then this becomes sigma of V bar. What is sigma of V bar? We can use this first representative of V bar. So, then we can see that sigma of V bar is nothing but sigma P R alpha. So, that means sigma P is P. So, then this fixes P R alpha, which is exactly V bar. So, this proves that tau fixes each element inside this capital V, which is E modulo R alpha, and it also fixes alpha. So, that means tau has only one as eigenvalue. So, the only eigenvalue of tau is 1. Of course, counted with multiplicity, it will be dimension of E. So, then it means the characteristic polynomial of tau must be x minus 1 power dimension of E. So, now this implies that the minimal polynomial of tau must be x minus 1 power r for some r that is at most dimension E. Okay. So, one hand we get this. On the other hand, we can see that this tau actually fixes leaves phi invariant. So, that but phi actually spans this capital E, okay, because sigma leaves phi invariant, S alpha also leaves phi invariant. So, that makes this tau to leave this phi invariant, and span of this phi is actually capital E. So, these two things are given. So, from that we can actually again compute the action of tau, in particularly the minimal polynomial of tau. So, let us take some beta in phi and then observe that this beta, tau square beta and so on, this cannot be all of them distinct, okay, because all these are elements of capital phi and capital phi is finite. So, that forces that there exists some power I and j such that this tau power I beta must be equal to tau power j beta. So, then you can actually assume to be I greater than or equal to j, So, then you can see that tau power I minus j beta must be equal to beta. And since phi is finite, so this forces that there exists some large k such that tau power k beta is beta for all beta in phi. And since phi actually spans, so span of phi is equal to capital E. So, that forces that tau power k is identity on capital E. So, this means the minimal polynomial of tau must divide tau power k, sorry, x power k minus 1, x power k minus 1. But we have already observed that the minimal polynomial of tau already divides x power minus 1 power dimension e. So, that means the minimal polynomial of tau must divide both x power minus 1 power dimension e and x power k minus 1. But you can see that they are actually the only polynomial that divides both of them is nothing but x minus 1. Thus, that forces that the minimal polynomial of tau is divides x minus 1. Okay. So, that means, so the minimal polynomial actually should be non-trivial polynomial. So, it is non-constant polynomial. So, that makes it actually the minimal polynomial of tau is equal to x minus 1. So, that forces that tau must be identity on E. So, that is what we wanted to prove, because tau is nothing but sigma s alpha. So, that forces that sigma equal to s alpha. Now, since sigma is s alpha and sigma fixes this capital P and s alpha fixes this capital P alpha. So, that forces that those two hyperplanes P and P alpha must be same. So, this actually ends the proof of this lemma. So, this lemma again will be very crucial, and it will be used again and again later in order to understand isomorphism between phi or automorphism between phi and so on. So, what it says, let me repeat. You start with a finite set that spans E. For example, you can take phi to be a finite root system. So, suppose if you assume that S alpha phi is phi for all alpha in phi, and there is a sigma in GL of E that leaves phi invariant, that fixes pointwise a hyperplane P of E and sends some non-zero alpha in phi to its negative. So, then we can conclude that sigma must be equal to S alpha, and in particularly P equal to P alpha. Okay. So, we will see some consequence of this result later. So, I will actually stop now because we are running out of time. I will continue with more properties of root system in the next class. So, in particularly I will actually classify the rank 2 and rank 1 root systems, which will actually serve good examples of root systems. Okay, I will stop here. Thanks.